Okay, super. Well, thanks for having me and thanks for the invitation, Greg. I'm going to warn you ahead of time that I'm not actually going to tell you very much physics. Um, there's such a potpourri of stuff that we're doing that I thought it would be more fun to kind of just look at all the things rather than dive that deeply into any of them. So just fair warning. Um, we are an all undergraduate institution. So there we go. We have a lot of undergrads who I need to thank for doing most of this work. And the stuff that we're looking at is mostly tabletop scale, right? So these are kind of the scales that we tend to work at. We have sort of centimeter scale plasma, or we simulate stuff on the computer. And so that's also kind of centimeter scale. So what I want you to take away from the talk today is that non-equilibrium atmospheric pressure plasma, we'll talk more about sort of what that really means, is interesting. There's lots of questions. It's a very sort of multifaceted interdisciplinary field, which is really fun. And I'm also going to tell you something about a little more traditional piece of plasma physics, which is these non-axisymmetric force-free magnetic fields might actually have interesting confinement properties that we haven't seen before. And the last thing is that because I'm the only plasma relevant person at Colorado College, I'm always looking for other people to talk to about these problems so that we can actually have conversations and make progress. So if you're interested in any of this, please follow up with me. I'd love to chat about it. So on the way to those goals, we're going to talk a little bit about cold plasma. I'll talk about solvated electrons, which is sort of now become our main research focus, but has been a curiosity for like a century. And I'll talk about particle confinement in these force-free fields. Okay, so first, what is cold plasma? Technically, there is no agreed upon term for this stuff. So people will say non-equilibrium plasma, people will say no low temperature plasma, people will say non-thermal atmospheric pressure plasma. Anyway, here's just some examples. So these two, this is our plasma jet in argon at atmospheric pressure in our lab. This is just like a little DC discharge in ambient air in our lab. But there are also clearly other fun sources that people have made at atmospheric pressure. And basically cold plasma is just a low temperature gas discharge at atmospheric pressure, typically. You can make cold plasma at lower pressures, but this is mostly what people mean. Because it is at atmospheric pressure, it's usually transient. What's interesting about it is that electrons have enough energy to actually do stuff, right? They can break chemical bonds, they can sort of precipitate things with a high energy barrier, but the ions and neutrals are near room temperature. So there's basically no heat, right? So you can apply cold plasma to delicate materials and do interesting things without damaging the material thermally. The collision frequencies are very high, right? So at atmospheric pressure, like electron neutral collision frequency is like a terahertz, right? So that means fluids, like we might be able to model pretty well with fluids, but the problem is that these plasmas are so transient that the distributions are almost always not in thermal equilibrium. And so fluid models might not work at all. So it's an interesting regime to think about physically. And you can do lots of cool stuff with it. So some of the things that are big chunks of cold plasma research are surface modification. So if this is sort of a crappy diagram of a polymer being cleaned and prepared for some purpose by cold plasma. So you can have ions that bombard it, you can have electrons that attach to the surface, you can charge the surface, you can sort of leave dangling bonds, or you can attach new surface groups if you want to modify the chemistry. The picture at the right is actually from a plasma agriculture project that's about sort of decontamination, right? So can you kill like cholera on vegetables without damaging the vegetables? And it turns out that you can, at least in some circumstances. So there's a lot of applications. Here's just a couple more to show you, kind of take us a little closer to what we were doing. This is formation of gold nanoparticles, which is usually done by like a reductive chemical process, and it has some pretty nasty outputs and inputs. And so it's actually sort of a greener way to make gold nanoparticles, which are really sort of commonly and widely used in chemistry with cold plasma. And the one way to reduce those gold atoms and make them clump up is by introducing electrons directly into the fluid. And so that's the process that we're mostly going to talk about in terms of the cold plasmas. But here's just a little glimpse of kind of two sets of chemistry. And this is one of the things that's great about cold plasma is it is really easy to make. But the thing that is hard about it is it is really complicated and difficult to measure. So we're mostly going to be over here in the sort of water liquid chemistry. And there's sort of three regions that we tend to talk about, right? There's the plasma or gas phase. There's the liquid phase, and then there's the interface. And the interface is kind of where all of the interesting stuff that we are looking at happens because of the small time and space scales. So that plasma liquid interface is kind of a big deal at the moment because that's where all of the stuff we don't understand is happening. Okay, so here's just a quick sort of list of some of our projects. So the most interesting cold plasmas for a lot of applications are the most transient, right? So if you turn on your electric field for only a few nanoseconds, you accelerate electrons like crazy, but the ions haven't moved at all, right? And so you can have this like strong electron ion non-equilibrium, and you can dump all the energy into the electron channel. And so you can be very efficient about where you put that energy. But the problem is that it's really hard to generate these high voltage pulses so quickly. So just for reference, right, if you've, I don't know how many years it's been since you've done electronics, but typical op amp, right, a nice-ish op amp can slew like a kilovolt per microsecond, right? But we're trying to get rise times of like 10 kilovolts in a nanosecond, right? So it's much, much harder to generate those high voltage pulses than typical circuits would make you think. So you can either pay a lot of money for a carefully engineered box where they've basically empirically moved all the things around to tune all the capacitances and inductances so that you can get a short rise time. Or you can use a really cheap spark gap, but you have no control of the timing, right? So a spark gap is actually a pretty great fast rise time switch, right? But you have no control. So typically, triggered spark gaps, nice triggered spark gaps, use a high energy laser to ionize like the middle of the gap, right?
Sorry, when you say no control, you mean no control at the nanosecond time?
Yes, 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 yes.
You've got microsecond control.
Yes, but we don't have control at the timing level that we need to actually study what we want. Yeah, yeah, you're right. I'm being a little bit flippant about the utility of spark gaps, mostly because of our frustrations. But yeah, so typically a triggered spark gap needs a very high intensity laser because you have sort of an anode and a cathode that you're holding below the breakdown threshold of that gap. And then you ionize in the middle. And so you cut the gap in half, right? And then you can get breakdown that's very precisely timed. Those are expensive, so it doesn't help us, right? Instead, we found an abstract that was never developed from somebody in Hong Kong in like 2006 that was trying to use a UV LED to trigger spark gap. So we wrote to this person and we're like, hey, this is cool and interesting. Like, did it go anywhere? And he said, no, it never got funded, so I never pursued it. So one of the nice things about working with undergrads is that we sort of have the luxury to try risky science, right? Because grad students are not depending on actual results. And so we thought, well, we can build one and try it. And so the idea is that rather than ionizing the gas in the gap, we're just going to seed breakdown by ejecting electrons from the cathode, right? So photoelectric effect. And if you do this densely enough, right? If you dump enough energy in a small enough area, you can actually produce sort of a critical density of electrons such that the electric field in front of that little blob of electrons is at least as high as the gap voltage or the electric field near the cathode, right? So you can essentially shorten the gap. And sometimes you can even exceed the gap electric field if you have a high enough density of electrons, right? Right in front of that bunch of electrons, you can get a high electric field, which will then break down the gas in front of that, and you get a little avalanche, right? And so the idea.
Sorry, just to be clear. So the plasma that you want to create is actually in the spark gap, or you're using the spark gap as a switch?
That's right.
For the main.
This is just an applications project. Yep. So this is kind of the drawing of our setup and what it looks like right now. So we have this UV LED that's like a watt, and we pulse it with a little laser diode driver, so we can pulse a couple amps for a watt or for a few nanoseconds.
What's the wavelength?
It is 270 nanometers. Yep.
I'm sorry,
So-
how many EV is that?
It's like 4.6, something like that, 4.5-ish. So we're just high enough that we can do this with aluminum, but it didn't work very well. And so we actually switched to these electrodes are lanthanated tungsten for welding. So they actually have a little bit lower work function, and we hope that'll help us to do this. The optics right now are our biggest issue because it's we need to focus this light down to a small spot, but the LED is kind of diffuse. So we're having trouble getting the power sort of concentrated as much as we want. Because what's happening at the moment, here's what it looks like in operation, at least in ambient air. And here's a little oscilloscope trace. The yellow, those are the current pulses that we send to the LED. And the blue is the voltage across the gap. So we can trigger the spark gap, sort of, right? We can make it so that the gap only discharges in time with the pulsing of the light, but we can't get it every time. So
I'm confused. The yellow is just a flat line.
oh, I'm sorry. Maybe I can zoom in here.
Little spikes
Can you
in
see
there.
the little spikes?
Oh, I see. Yes.
Yeah, so those are tiny little sub-microsecond width pulses of current that go to the LED. And so we can kind of constrain the discharge, but not really.
So this cadence, is the cadence random? Because, I'm just seeing one spark, and then a little decay, and then another spark. I can imagine that that's sort of like a recharging time,
Right.
and it could be regular.
We thought about that.
Okay.
But if you slow it down, you have the same issue.
So basically, there's kind of just a random cadence. It might
Yeah.
happen once every fifth or once every 10th or
Exactly.
whatever.
Yeah. And so rather than showing you sort of that whole pattern, I
Yeah.
tried to zoom in so you can see a little bit.
Sure.
So anyway, what we're trying to do now is understand a little bit more about how this is or is not working. So I have a student who's doing a little simulation where basically if you turn this vertically, we've got a little fluid simulation where anode is at the top, the cathode is at the bottom, and here's showing a few time steps kind of in the middle of that simulation where basically you just eject a blob of electrons at the beginning and watch it propagate, right? And so this is just a sort of all electron fluid simulation. So it's super simple. It may not actually be relevant, but this is sort of like our first step to try to figure out what's happening. We do actually see the contours there at the top show you kind of that blob of photoelectrons, right? That propagates toward the top. And the right-hand panels on all of these, so the left-hand panels are electron density, right-hand panels are the difference from the initial gap electric field, right? Which points downwards. And so you can actually see enhancement of that electric field, right, in the gap as we sort of go along. And then after that blob hits the top, we kind of lose that enhancement. But if you plot the electric field sort of right about here, about 0.8 millimeters above the cathode, this is what it looks like. And so we think, right, if this is actually relevant physics, right, once we start developing more complications and having collisions and things that actually matter, if we can maintain this kind of electric field enhancement, then we think we can actually produce sub-threshold breakdown pretty reliably, right? Because in this gap, there's a kilovolt per meter electric field to start with, right? And so if we can enhance that by a factor of 4, even transiently, right, we can start that breakdown. And so we think this is still a good project to be working on. But it's, it's slow. We have one undergrad and we're going along. Yeah, question.
So from just from the point of view of just like a lab tinkerer, my impression when I see that plot where you're hitting it sometimes, you're triggering the spark gap sometimes, I'm thinking to myself, okay, so you have marginally enough electrons.
Yeah.
And so, just get a second LED and then
Mhm.
you'll just whack it and you'll
Yep.
have reliability.
Well, so that's when I said our challenge right now is optics. That's part of it, right? So what we're trying to do is clump several of these high current LEDs in a small enough space,
Right.
that we can collect the light from them reasonably, and then focus that light, right? Because what we started out with is a like a light pipe that's like 5 millimeters. But the problem is that when you try to image that down into a very small spot, it's not a point source. And so it's hard to get that light concentrated. And so we're trying to switch to a fiber delivery system so that we can do that a little better. And we have to keep the LED separated from the gap because otherwise we get crosstalk. So anyway, we think it's possible and we're going to keep working on it. But that's sort of one of the things that we're doing. And it's basically can we do this atmospheric pressure stuff more cheaply and easily, right? And so several of the projects that we've got are about that. One of the other things that I'm particularly excited about is trying to make a measurement that's easier. So right now, one of the ways that people measure electron density and electron distribution in atmospheric pressure plasmas is by spectroscopy, right? But you need a lot of modeling for that, right? So you have some big collision radiative model, or you have some other way, right, of kind of trying to get at the spectroscopic signatures of that electron density, right? And that turns out to be pretty hard, at least for someone who's not a spectroscopist by training. But in principle, you can still use interferometry to measure the electron density, right? Just like anywhere else. The issue is that the electron density is very small. So in our plasma jet, we think the electron density is something like 10 to the 12 electrons per cc. So that's like 10 to the 18 per cubic meter. So if you calculate that out, we use 405 nanometer light to try this so that we can get as big a phase change as possible. But even if you do that, you're looking at a microradian phase shift. It is minuscule. So what we're trying, we think it's possible. We haven't made it work yet, but what we're doing is using a lock-in amplifier and careful timing to kind of get the laser, right, to do sort of a stroboscopic sampling of the plasma so that we can get time resolution in principle, right? And the timing sort of allows us to eliminate noise sources, right, that are not exactly at the rate we're measuring. Right now, I have some undergrads working on getting a tight focus because these plasmas are like millimeter scale, right? And so if you want any spatial resolution in your interferometry, you also need a really tight laser spot that you can then move around carefully in the gap to figure out, right? So we're testing this right now with the spark gap because it has a much higher electron density that we think we can for sure see. But I'm pretty excited about this because if we can develop it, it will open up a lot of opportunities for measurements at pressure. One of the other things that I've got students doing right now is very applied. It's surface modification. So a lot of, in the semiconductor industry, especially, a lot of surfaces are modified by inductively coupled plasma at low pressure. But this is true also for things like polymers. So a lot of things like biological well plates are plasma treated so that cell cultures will adhere to them better because they don't want, the super hydrophobic surface where that cell culture just sits on the plate, right? They want it to actually attach. So here's little pictures of a piece of polystyrene that we treated for 10 seconds with our plasma jet. And you can see that the contact angle of that drop of water changed significantly, right? So we can actually make that surface much more wettable with just argon plasma in ambient air, which is cool, right? Because it's super cheap and easy and accessible. So right now we're actually testing this with a biology colleague of mine upstairs to see if we can make well plates that her biofilms will grow better in. So that's been kind of fun. And at some point, if we can sort of make it work well enough that we want to understand, then we'll do some surface relevant measurements like Raman spectroscopy or FTIR or something to figure out like what are we actually doing to that surface. Question?
Let me this is more of a suggestion than a question. But if you ever do it, sometimes one does experiments and you get literally like the opposite effect of what you're looking for. And the inclination is to think, oh, what a failure. But I just want to tell you that there are also tons of applications for modifying surfaces so that stuff doesn't grow.
Right.
So if you're having
Absolutely.
to do something that goes in the opposite way, don't
Totally.
throw it away.
Yeah.
Equally
So
important.
what we're seeing actually so far is we can change the wettability, but it doesn't make the biofilms grow better.
Yeah.
In fact, it does absolutely nothing, but we think, and we need to do like an actual study on this because we weren't thinking about it at all, that even though the biofilm grows the same, the cells are less viable in the plasma treated wells. So we actually might be inhibiting those cells in some way with the treatment, but we don't know what it is, right? And so this is exactly that situation, right? Where like it's the opposite of what we thought, but it is interesting and useful. Okay, so
How long does this surface modification last?
good question. It is transient, at least at the precision we can measure it. So if you watch the contact angle, it will recover over about 48 hours. So, you know, we can sort of keep it roughly like within 10% of the treated contact angle for about the first 24 hours. And then it starts to kind of recover. And that it's different for different materials. We haven't really tried sort of a lot of the parameter space in terms of the plasma. So I think there's a lot of work to be done there. But yeah, it's an interesting question. Yeah.
One more question, and then I'll leave you alone. Do you think that this is a chemical or a physical effect? You think you're affecting the roughness, or is it?
I think it's chemical. That's my suspicion.
Yeah.
So the way most of the wettability treatments work is by bonding oxygen groups or removing oxygen groups, because the electronegative oxygen likes to stick, like water will stick, right? Because it's polar. And so the more oxygen groups you can get, kind of the better water will stick to it.
So you're
At least that's my understanding of
like
the chemistry.
Rubbing off stuff from those bonds so that they're open to receive water.
Well, I think so that they are either open to receive water or so that they get things like you know, ozone that bombards the surface, then becomes some oxygen group attached to that surface. Right. But
Okay,
the
well,
chemistry
so it makes
is
a big difference because you could maybe put stuff in your plasma.
yes, absolutely.
Yeah. Okay.
Yeah. So one of the next things that these students are going to try actually is using humid argon, which will introduce exactly that, right? So like we don't have an oxygen bottle in the lab yet, but the humidification makes a huge difference, at least in the literature, right? And so we're going to play with that too. So anyway, this is just kind of a potpourri of stuff that that we have going on. But our main project is actually trying to measure electrons that are dissolved in the top layer of a fluid by a plasma. So this is a nice diagram from the only folks I know of who have done any of this science. They're at Notre Dame, David Go and Paul Brumbach. But the idea basically is that you can either bombard the surface with ions if you have a positive polarity electrode, and that will ionize some stuff at the surface, or you can directly inject electrons into the liquid. And I didn't know that solvated electrons were a thing until about 5 years ago. But it turns out that you can, you know, put an electron in a liquid, and the theory right now is that a cavity of water molecules, at least in this case water, right, will form around that electron, and there's a bound state in that cavity. And so that electron can actually absorb or emit light, right? But the size of the cavity determines the energy of the bound state. And so different amounts of molecules give you different energies. And so there's this broad absorption feature for solvated electrons. If you do this in ammonia, you'll get a beautiful blue color, and the electrons stay around almost indefinitely. But in water, they last about a microsecond. So that's hard.
What happened to quasi-neutrality?
Oh, yeah. We'll come back to that if there's time. So these electrons are highly active, right? They have a reduction potential of almost 3 eV. So they're like very good at precipitating stuff to happen. They're thought to be major contributors in all this sort of plasma liquid chemistry. So there's a lot of, I didn't talk much about biological applications, but a lot of atmospheric pressure plasma is used for medical treatment sort of stuff, right? So you can disinfect a wound, you can promote healing, you can kill cancer cells like in situ. If you put a plasma through a biopsy needle, you will actually preferentially kill cancer cells because they are more susceptible to oxidative damage from the plasma species. And there's all sorts of good stuff, but it's all in this environment of plasma liquid contact. And so people think these electrons have a lot to do with what's happening, but nobody knows because there are very few measurements. The Rumbach group is actually the only group that I'm aware of that's made any measurements of solvated electrons produced by plasma. And our application, yeah.
Does that mean? I mean, are they pretty sure that this sort of solvated electron exists?
Yes.
They're not.
There are lots of studies of solvated electrons. Usually they're produced by pulse radiolysis. So you have some kind of high energy radiation, right, that you send through your liquid and you ionize it kind of in situ. And so you can produce these. But plasma production is much cheaper and easier. And so it's of interest.
And what is the binding energy in this state? Are we talking EV or?
Yeah, it is.
sub-EV?
It's of order 3 eV, depending on whether you're talking about sort of at the surface with a sort of partial cavity or all the way in the bulk. And there's details, but yes, it's EV.
Where do these electrons go in water? Is it like you end up with a?
Well, you close the
water
circuit
or-
somehow,
Okay.
right? And they either end up as ions, right, or as sort of right attached to something else,
Okay.
right? And then usually those ions are the things that carry the return current out of the water, right? So
Are you saying negative ions?
yeah. So I'll show you sort of what the whole system looks like in a minute.
Is that what happens after a microsecond in water, that the electrons attach?
Yes, exactly. Yep. So the application that's sort of driving our question, I don't know how many of you have followed the PFAS contamination issues in Colorado, but it's a big deal in Colorado Springs because this PFAS foam has been used on the Air Force bases since like the 50s and 60s as a fire suppressant. And now it's in the groundwater. And now we know that it is a problem, but it's a good fire retardant. It's super stable, never breaks down. It's really hard to incinerate, even if you get it out of the groundwater. And this is getting to be a major problem. So major that it was actually in the 2020 decadal report for plasma science, because plasma is so far the only path towards remediation that seems at all economically viable. So these things are a problem, right? And so far, plasma is promising. There's the group that's sort of leading the application charge here is Selma Taggart, Taggart at Clarkson. And so here's some pictures from her work. This is kind of what their system looks like, and they've built actually kind of a industrial scale treatment system that's in a trailer. And so they took it out to Wright-Patterson Air Force Base, and they took it some other places to actually treat real well water. And on the left, the vertical axis is percent removal, and the horizontal axis is a bunch of different PFAS compounds. And so they can actually do a pretty good job of removing, especially the center category there. These are the long chain PFAS molecules. The short chain ones are a little bit harder. Precursors are a little bit harder, but you can do this at a reasonable sort of flow rate, reasonable level of intervention in your system, right? But we don't understand exactly how it works. So one of the major proposals is that solvated electrons are responsible for this process. So here's just a computational picture of what they think a solvated electron probability density looks like. Right? And this is in a small cavity, right? So there's only a few water molecules here. But the idea is that fluorine is super electronegative. And so if you can put free electrons near those fluorines, then the fluorine picks it up, and that destabilizes the bond between the carbon and the fluorine. And so then you can kind of cleave it. The absorption spectrum of those hydrated electrons or solvated electrons, right, is, as I said, really broad. And so the Rumbach group actually measured discrete wavelengths here from a DC discharge to try to sort of show that these electrons actually existed. But the problem with this is, again, the lifetime is super short, right? So it's microseconds. And if you kind of play around, the estimate for how deep these plasma electrons actually penetrate into liquid before they attach to something else is only about 10 nanometers. So if you're trying to do an absorption measurement, your path length is of order 10 nanometers. And that makes your signal really small, even if you have a good absorber. So this is kind of the data from the Notre Dame group, their first measurements anyway. And you can tell from the error bars over here, this is the absorption. The curve is the sort of previous pulse radiolysis absorption curve for hydrated electrons. This is wavelength. That's absorption intensity that's normalized. And the data points here with the red error bars are their measurements. And so you can tell the error bars are pretty big. They're pretty close to the noise threshold. But they, I think, have made a convincing case that these electrons are there, right? So this is the way they sample it, right? So they have this argon plasma. There's the interfacial sort of vapor layer, which is a whole other complication. And then there's this 10 nanometer layer where we think those electrons are produced. And the idea is basically you send a laser beam off the surface from underneath and you get total internal reflection. So you sample all the way to the surface, then you're sure you've captured that 10 nanometer layer and you can do it twice. So you kind of get a little boost there. The problem with this measurement, right, is that it is DC, so it measures the average concentration of electrons with all of these sort of like sources and sinks, right, which makes it hard to tell what's happening. And it's a very time-consuming measurement because you're doing one wavelength at a time. So what we've recently been funded by NSF to try is to solve those two problems. So we're developing a similar measurement that uses a supercontinuum. So we're going to sample a broad band of wavelengths at the same time. It's pulsed, so we can localize our measurement in time, right? And we're going to use lock-in detection, just like the Rumbach group did. I forgot to mention that, but we're going to use multi-channel lock-in detection so that we can essentially get the spectrum all at once, and we can have stroboscopic time resolution. So I'll show you a little bit about how that works. So this is kind of what the timing setup is like. So if you imagine you have a laser pulse, right, that's maybe has a megahertz rep rate. We set the high voltage pulse rate so that the discharge from our like nanosecond scale, you know, it's maybe 100 nanosecond long plasma discharge, only lines up with that laser pulse every like third or fourth or some integer number of laser pulses. And that means that we can actually look at the lock-in signal at that slower rate rather than at the laser rate or at the discharge rate. And the reason that that's important is that if you just try to do this measurement with your lock-in amplifier at the plasma pulse rate, it's hopeless. The nanosecond pulsar that we have, the $35,000 one, if you just put the leads across a resistor and you put a little coax breakout cable about 2 meters away, you'll get 10 volts of pickup on it. It's awful. There's so much noise. So, but we think we're able to get around that by doing this sort of careful timing. And then you can also change sort of the relative delay, right, between your high voltage pulse and your laser pulse so that you can sample, right, the laser pulse is only about 100 picoseconds long. And so we can sample pretty precisely inside that 100 nanosecond discharge. And so we think we're able to get time resolution in principle. So this would be huge if we could actually understand what happens as a function of time, right, as these electrons enter the liquid. And the eventual goal is to understand what relationship that has to the electron energy distribution function in the plasma so that you can kind of optimize your plasma for whatever application, right? And that's kind of the idea. So here's just a little bit more detail about the system. This is our supercontinuum spectrum. So this is logarithmic power on the y-axis and wavelength on the x-axis. And in case you can't see, it goes all the way from 400 to 2400 nanometers. So this is kind of an incredible instrument that 10 years ago would have been 10 times as expensive to acquire. But now you can buy a commercial turnkey source like this for about 20,000 euros, which is kind of amazing. We're restricting the bandwidth because as much as we would like to measure the whole thing and we have the light to do it. It turns out doing this sort of spectral dispersion with prisms is kind of tricky because it's nonlinear with wavelength. And so we decided to just pick a 1-octave bandwidth and use a grating, and then our orders don't overlap. And so this is what our system kind of diagram looks like at the moment. So this EHT is a Eagle Harbor high voltage nanosecond pulsar. The ice blink is our supercontinuum source. We have an FPGA based 16-channel lock-in, and we have this surprisingly nice timing delay generator that for about $1,500, if you're looking for one, we got one for about $1,500 used, and it goes down to a 250 picosecond precision in setting relative timing, which is totally wild. And we're right now, we don't have the full system operating yet. We have everything except our detector. So we're actually using a photodiode array. And so I have a student building a little transimpedance circuit to get that photocurrent into a voltage that we can then actually measure on our lock-in amplifier. So that's where we are with that project. And I'm pretty excited about it because I think it's, again, it's a high risk, high reward project. But the students like working on it. My daughter loves it because there's a rainbow laser involved. And if we are able to succeed, it could be really huge for understanding what's happening in these systems. Okay, so that's kind of the stuff that we're most actively doing right now at Colorado College. But I also have this ongoing project that mostly I wanted to tell you about so that you can help me answer these questions that we have. Scott, you were mentioning Mike Brown at Swarthmore has had this experiment going for 25 years that was originally focused on reconnection, but is able to produce these compact toroid objects, right? Spheromax in coaxial guns that you then shoot into sort of different shapes of copper flux conserver, and they relax to some particular equilibrium, right? And so over the past 25 years, they've figured out a lot about this, right? That they can produce these various sort of MHD force-free states. And I didn't put any MHD in the talk, but in case you haven't come across these before, it's basically if you have J parallel to B, then J cross B is 0. And so there's no Lorentz force, right, maintaining the equilibrium. And this is kind of this is an old Slava Lukin simulation, I think, of that process. So you launch a spheromac from one end of a long cylinder, and it tilts over and then kind of wraps up. And this process, we think we understand how this happens, that it's basically conservation of helicity. So if helicity is better conserved than energy, then small fluctuations can basically move the currents around and dissipate energy until you end up with the lowest energy state for those boundary conditions that still has the initial helicity that you injected. So this is what the final configuration looks like. And it turns out that it's actually very, this sort of force-free MHD is very good at predicting the structure of this object, right? So if you actually go into the machine and you measure it, right? So these aren't quite aligned, so don't compare too carefully, but it's very successful, right? And if you're interested in the measurements, they're good papers from about 8 or 10 years ago. But what we realized in the last few years, so here's just another picture of that same magnetic field structure. So this is the minimum eigenvalue for curl B equals lambda B, if you're an MHD nerd, in a 10-to-1 aspect ratio cylinder. So this is the self-organized equilibrium that we think we are producing in the experiment. And MHD works really well for describing this, right? But the problem is the particle orbits are big. So MHD shouldn't work at all, right? And so we realized this recently and we thought, oh, well, maybe we should actually figure out what's going on here. And we opened a huge can of worms and now we have a lot of questions. So we kind of foisted this onto a student at Swarthmore when I was there and said, hey, why don't you write a little Boris stepper and simulate some particle orbits? And we thought, okay, well, maybe we'll find some interesting things. Turns out there are lots of interesting things. One is that the particle loss is surprisingly logarithmic. So on the left here, this is the percentage of initial particles, right, that we started with that they're still confined at a particular time step. And this time coordinate is in sort of thermal Larmor orbit periods, right? So if you choose, these are protons. But question?
Just real quick, what is causing the loss of confinement?
Right.
I mean,
So
in your simulation, what's causing it?
anything that exits the boundary, right, that hits the wall of the flux conserver has disappeared, and we call that escaped.
Okay,
So
that's it's walking out ideally. Is it ideally? I mean,
yes, there's no collisions.
There's no
Yes.
collisions. Okay, so it's just wandering.
It's just
out,
wandering
following
in the field.
Okay,
That's
got
right.
it. Thank you.
Yeah. And so this is sort of like a first crack at this problem, because we thought, oh, well, maybe we'll learn a little something interesting, but it's mostly an undergraduate problem, right? That someone can learn to play with simulation with. But it is interesting. So if you look at how, like, the fraction of the particles that you lose on a logarithmic scale, you get this crazy straight line over here. And I'm going to show you why I don't care about this little curve. This is the time at which 50% of the particles have escaped, right? And that's about right here. So basically, all of these particles we think are essentially too close to the edge or have too big a Larmor orbit to start with. And so they basically ballistically exit the volume. So we don't really care about those particles in terms of understanding the confinement of the particles that are left, right? But this is really puzzling. I have not, so far, not come across any model that would predict this kind of like logarithmic loss rate. And so my suspicion is that there's not anything complicated about it, and it just has to do with kind of like, you know, how the particles end up exposed to the wall and how they get close to it and stuff. And but we really don't know what's happening. But as physicists, right, we saw the straight line and we were like, something's happening here, right? Something's going on. Question?
Well, just real quick. So I mean, are these non-interacting particles,
Yep.
or are they interacting particles?
Non-interacting.
Is there a distribution function? For
There
it?
is. They
Are you
start.
just losing the high energy ones first?
I'm glad you asked that.
Next slide.
Yes.
Yeah.
And so there are trends, but there's no clear separation between the particles that escape and the particles that don't. Okay. So in these charts, escaped early means in the first half, right? The first half of so before that T50. So those are the particles that basically escape immediately. Then the ones we actually care about separating are the sort of purple or blue and red, right? Those are the ones that are confined for the entirety of the simulation, right? Versus the ones that escape somewhere in between. And we think, I didn't actually put this plot in here, but we think we have a long enough simulation, because if you look at the average energy of the particles that are contained, it goes like this until you get past about T50, and then it's pretty steady. Question?
Well, I mean, maybe I'm just interrupting your talk, but you know, clearly, the question, you know, the obvious questions to ask are like, you know, if you slice it up versus energy, or if you slice it up versus pitch angle, or if you slice it up versus location in the device. And so, anyway, I'm just asking.
Yeah, and I can show you all of those charts, and all of them show something, but not anything particularly compelling. So, for example, we thought, well, maybe it's just the particles that, like, you know, the gyro radius goes all over the place as they trace out this field. So maybe that's what's happening, right? And so we thought, well, maybe if we just look at the particles that spend more time where they have a big gyro radius. And so if you do that, this is not up-to-date labeling yet, but the red is ones that escape in about the first third of the simulation. The yellow is in sort of the first second third of the simulation. The gray is in the third third of the simulation, and the blue are the ones that remain confined for the entire simulation. So yes, it matters, but there's not like a clear separation. Same thing with location, right? So if you look at the percentage of particles, so this is our grid where we started, and at each of these points, we started 100 protons with a thermal distribution, and just follow them until they leave or don't leave, right? But we ran essentially as much computer time as we had.
And random pitch angle?
Yep, random pitch angle, random for each location, right? So we didn't use the same set of velocities for each location. So we sampled a lot of the parameter space there. And stuff that starts closer to the center, stays confined longer. And so if you're just following the field lines until you get close enough to the edge, that would make sense, right? So maybe there's not anything more complicated. That kind of makes sense if you look at where the particles exit as a function of when they exit, okay? So these locations are points on the surface where the last coordinate of the particle was before it hit the wall. And the color is how long it took to get there from the initial start of the simulation, right? So the purple, those are, 100 orbits or something, and T50 is like 200 orbits. So these clumps right here are the particles basically that started right too close to the edge or with too big an orbit, and they ballistically went to the wall. But the rest of them seem to kind of propagate along the field and squeeze out in between the flux ropes, right? So this equilibrium kind of looks like a skein of yarn, right? If you have sort of two twisted flux ropes, and the particles seem to squeeze out in the gaps between those flux ropes, which is interesting. We don't know what it means. But the most interesting thing that we saw is that some of the confined trajectories describe really compelling surfaces. So I've removed some of the field lines in here so you can see the structure. But this is an orbit that we simulated for another, so this is 10,000 orbits, fiducial orbits, right? Thermal proton orbits in the normalized sort of B0 field. We took this one particle and we simulated it for another 10,000 orbits, and it just retraced this surface, right? So it's clearly trapped in some sense, right? And it's not just that we didn't simulate it long enough. We were thinking like, oh, well, this is interesting. Maybe it's a flux surface. But it's hard to define because we have no axisymmetry. So flux surfaces technically are allowed, but they're not guaranteed. And, or I should say, but with flux surfaces, right, you expect some invariance, right? Like the canonical momentum is preserved and some of the other things are preserved, right? None of that is conserved on this particle trajectory. So everything we could think of, we took and calculated for this particle and plotted it as a function of time. None of it is steady. Question?
So have you tried like just as a test, setting the Larmor radius to go to 0 and seeing if it's still?
That's an interesting idea. We haven't, but looking at sort of like the guiding centers is something that we've thought about for sure. But our intuition is so stood on its head by some of the stuff that we're seeing that we're not exactly sure what question we even want to try to answer first. So for example, with this same particular orbit, if you look at it, you kind of think like, oh, well, maybe it's going and it's mirroring here and it's going back and forth. And it kind of looks like you could use the sort of usual adiabatic invariants to kind of categorize, right? Use drifts and stuff, but you can't. Because the places where the particle turns are actually minima in the field, not maxima. So it's not mirroring, at least not in the classical sense, but the turning points are where there's a strong gradient in the field magnitude. It's just in the wrong direction. So we don't understand, right? And so like, it's possible that it's just some quirk, right, of this geometry and the way the Lorentz force happens to line up, right? Kind of seems like the particles go along one way on one side of one flux rope, and then they get to the edge and the Larmor radius gets bigger and they kind of get captured by the other flux rope and they go back down the side of the other flux rope, and then that repeats. But we don't really know. Even if you look at a more, what initially we thought was sort of like a standard or sane orbit. So like this one, we saw this and we were like, oh, cool, this is just like a dipole, right? So you've got mirroring, right? So if you, I should have put a slide in about the dipole, but if you think about a dipole field, right, the electrons in a dipole field around Earth or something, say, right, they spiral around in their Larmor orbits, they bounce between the poles, right, mirroring, and then there's this azimuthal drift. And so we're like, oh, cool, look at this beautiful mapping. There's, bouncing and there's azimuthal drift, and this is going to look so great. But the problem is the field is weaker at the places where it turns. So it's doing exactly the same thing as this crazier orbit, and it is not obeying any of our usual sort of intuitive models. So we are confused. And if you have any ideas, I would love to hear them because I'm super curious about this. And so again, this is an undergrad project. And so we have maybe, 100 hours of undergrad a year to kind of poke around at this simulation. But it is fun and interesting. And so what we're trying to think about right now is sort of like, why would the particle loss be so predictable, right? The loss rate. What particle properties actually predict whether it's going to stay in the volume or not? And what are these surfaces, right? What describes them? They're, we have no invariants to work with that we are convinced by at the moment. So it's a very interesting little problem. And it's a nice way, I think, for some of our students who are a little more computationally inclined or ones who are interested in a little bit more traditional plasma physics stuff to kind of get them started there. So that's that project.
So, one of the things that people do, computationalists do, and theorists do, when you're dealing with more standard geometries, is to remap things into some sort of coordinate system. Like, you're probably doing this in Cartesian coordinates because it's such a crazy mess. But
Absolutely.
I'm wondering if there's any way to somehow, I had an electronics professor one time that told me every physical effect is linear as long as you have the right graph number.
Yeah.
And so that's sort of what I'm after.
Absolutely. Right. So like, I was talking with Eve Stenson at the DPP meeting because she's sort of accelerator person about how, sort of those twisted helical coordinate systems and sort of like, where's a good place to start with that? Because we also had the thought that, maybe if we can unwrap this and understand what those coordinates are, then maybe that'll help us figure out sort of what these surfaces are following, right? Because our initial idea was like, oh, cool. Maybe these are, surfaces of constant, I don't know, canonical momentum or something like a flux surface, but they're not. And so at least not yet, right? So maybe we'll discover that some particular combination is invariant and we'll actually figure something out. But so far, we haven't gotten there. So I hope what you've been able to take away from this is that, we can do lots of interesting stuff with undergrads. And if you're interested in talking with us about any of these problems, we would love to have you. So, thanks.